The interpretation of the National Electrical Code, or NEC, regarding grounding electrode conductor, or GEC, sizing, specifically concerning Section 250.66 and Table 250.66, requires careful consideration. The situation arises when a grounding electrode conductor is connected to a ground rod, and the question is whether the entire conductor needs to comply with Table 250.66 or if a reduced size is permitted based on 250.66a. The correct interpretation is that 250.66 provides an exception for the portion of the grounding electrode conductor that serves as the sole connection to a grounding electrode, such as a ground rod. If a copper grounding electrode conductor is connected to a ground rod that is at least 8 feet long and driven to a depth of at least 8 feet, then the portion of the conductor that is in direct contact with the ground rod does not have to be larger than /6 American wire gauge, AUG, copper. It is important to emphasize that this exception only applies to the section of the conductor that is physically connected to the ground rod. The remainder of the grounding electrode conductor, that is, the portion that runs from the service equipment to the connection point with the ground rod, must still comply with the requirements outlined in Table 250.66. Table 250.66 dictates the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. To determine the appropriate size of the grounding electrode conductor, you must first identify the size and material of the service entrance conductors. Service entrance conductors are the conductors that bring power from the utility company's transformer to the building's service equipment. Once the service entrance conductor size is known, you can refer to Table 250.66 to find the corresponding minimum size for the grounding electrode conductor. For example, if a service is supplied by 3 parallel 500 kilo circular mills, or kc mill, copper conductors per phase, the equivalent total conductor size per phase would need to be considered to properly size the grounding electrode conductor. According to Table 250.66, a service with this conductor size requires a minimum /2 AWG copper grounding electrode conductor. It is vital to understand that the exception provided in 250.66 does not override the general requirement of Table 250.66 for the main portion of the grounding electrode conductor. The grounding electrode conductor must be sized according to the total ampacity of the service conductors, ensuring adequate capacity to safely carry fault currents back to the source. If the engineer stated that the grounding electrode conductor does not have to be larger than /6 AWG copper simply because it is connected to a ground rod, that response is not entirely correct. While the portion of the conductor connected to the ground rod can be /6 AWG copper, the main portion of the grounding electrode conductor must still meet the sizing requirements of Table 250.66. Therefore, in the scenario with 3 parallel 500 kc mil conductors per phase, the grounding electrode conductor should be a minimum of /2 AWG copper, except for the portion directly connected to the ground rod, which can be /6 AWG copper. To summarize the key points, firstly, Section 250.66 allows for a reduced size grounding electrode conductor, specifically /6 AWG copper, only for the portion directly connected to a ground rod that is at least 8 feet long and driven to a depth of at least 8 feet. Secondly, the remainder of the grounding electrode conductor, from the service equipment to the ground rod connection, must comply with Table 250.66. Thirdly, Table 250.66 requires the grounding electrode conductor to be sized based on the size and ampacity of the service entrance conductors. Failing to comply with these requirements can lead to inadequate grounding, which can compromise the safety of the electrical system and increase the risk of electrical shock or fire. It is essential to adhere to the NEC guidelines and ensure that the grounding electrode conductor is properly sized and installed. Additional considerations include the material of the grounding electrode conductor and the type of grounding electrode used. Table 250.66 provides sizing requirements for both copper and aluminum grounding electrode conductors. The choice of material will affect the required conductor size. For example, an aluminum grounding electrode conductor will typically need to be larger than a copper conductor to carry the same amount of current. The type of grounding electrode also plays a role in the overall grounding system design. Ground rods are just one type of grounding electrode. Other options include ground plates, underground metallic water pipes, and concrete encased electrodes, also known as UFERs. Each type of grounding electrode has its own specific installation requirements and considerations. When using a ground rod, it is important to ensure that it is driven deep enough into the earth to provide a low resistance connection to ground. The NEC requires ground rods to be at least 8 feet long and driven to a depth of at least 8 feet. In some cases, multiple ground rods may be required to achieve the desired grounding resistance. Underground metallic water pipes can be used as grounding electrodes if they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. Plastic or insulated coupling should not be used in a water pipe within 10 feet of the point where it is used as a grounding electrode. Concrete encased electrodes, or UFERs, are typically installed during the construction of a building. They consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. UFERs provide a very effective grounding electrode and are often used in areas with poor soil conductivity. In addition to the grounding electrode conductor, the equipment grounding conductor, or EG, is another important component of the grounding system. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse into energizing the faulted circuit. The equipment grounding conductor must be sized according to Table 250.122 of the NEC, which bases the conductor size on the rating of the overcurrent protection device. It is important to note that the grounding electrode conductor and the equipment grounding conductor serve different purposes. The grounding electrode conductor connects the electrical system to the earth, providing a reference point for voltage and helping to stabilize the system. The equipment grounding conductor provides a path for fault current to flow back to the source, protecting people and equipment from electrical shock and fire. The NEC provides detailed requirements for the installation of grounding and bonding systems. It is important to follow these requirements carefully to ensure the safety and reliability of the electrical system. Grounding and bonding are critical aspects of electrical safety. A properly installed grounding system helps to protect people and equipment from electrical shock, fire, and other hazards. By understanding the requirements of the NEC and following best practices for grounding and bonding, you can help to ensure the safety and reliability of electrical systems. Some common mistakes to avoid include incorrectly sizing the grounding electrode conductor, failing to properly bond metallic enclosures, and using improper grounding methods. It is always best to consult with a qualified electrician or electrical engineer if you have any questions about grounding and bonding. In summary, the grounding electrode conductor must be sized according to Table 250.66, with the exception that the portion connected to a ground rod can be #6 AWG copper if the ground rod is at least 8 feet long and driven to a depth of at least 8 feet. The equipment grounding conductor must be sized according to Table 250.122. Proper grounding and bonding are essential for electrical safety. Always follow the requirements of the NEC and consult with a qualified professional if you have any questions. The grounding system's effectiveness is also influenced by the soil conditions surrounding the grounding electrode. Soil resistivity, which measures the opposition of the soil to the flow of electrical current, can vary significantly depending on the type of soil, its moisture content, and temperature. High soil resistivity can impede the flow of fault current, reducing the effectiveness of the grounding system. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve the desired grounding resistance. The NEC does not specify a maximum grounding resistance value, but it is generally recommended to keep the grounding resistance as low as possible, ideally below 25 ohms. Regular testing of the grounding system is also important to ensure that it is functioning properly. Ground resistance testers can be used to measure the resistance of the grounding electrode. If the resistance is too high, the grounding electrode may need to be replaced or additional grounding electrodes may need to be installed. Bonding is another critical aspect of electrical safety. Bonding involves connecting all metallic parts of an electrical system together to create a low impedance path for fault current. This helps to ensure that all metallic parts are at the same potential, reducing the risk of electrical shock. The NEC requires that all metallic enclosures, raceways, and equipment be bonded together. Bonding jumpers are used to connect these metallic parts together. Bonding jumpers must be sized according to Table 250.102 of the NEC. The size of the bonding jumper depends on the size of the circuit conductors. Improper bonding can create a hazardous situation. If metallic parts are not properly bonded, they can become energized during a fault, posing a risk of electrical shock. It is important to ensure that all bonding connections are tight and secure. Corrosion can also affect the integrity of bonding connections. It is important to protect bonding connections from corrosion by using appropriate corrosion-resistant materials. In addition to the grounding electrode conductor, equipment grounding conductor, and bonding jumpers, surge protective devices, or SPDs, are also an important part of a comprehensive electrical protection system. SPD protect electrical equipment from voltage surges, such as those caused by lightning strikes or utility switching. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at any other locations where sensitive electronic equipment is located. The NEC provides requirements for the installation of SPD. It is important to follow these requirements carefully to ensure that the SPD are properly installed and will provide adequate protection. A well-designed and properly installed grounding and bonding system is essential for electrical safety. It helps to protect people and equipment from electrical shock, fire, and other hazards. By understanding the requirements of the NEC and following best practices for grounding and bonding, you can help to ensure the safety and reliability of electrical systems. It's crucial to consider the specific application and environment when designing a grounding system. For example, in healthcare facilities, the grounding requirements are more stringent due to the sensitive nature of medical equipment and the potential for patient contact. Similarly, in industrial environments with heavy machinery, robust grounding systems are necessary to handle large fault currents. Regularly inspect and maintain the grounding system to ensure its continued effectiveness. Check for loose connections, corrosion, and physical damage to grounding conductors and electrodes. Periodically test the ground resistance to verify that it remains within acceptable limits. Keep accurate records of all grounding system inspections, tests, and maintenance activities. These records can be helpful in troubleshooting problems and demonstrating compliance with regulatory requirements. Staying informed about the latest updates to the NEC and other relevant standards is essential for electrical professionals. The electrical codes are constantly evolving to reflect new technologies and best practices. Continuous education and training can help you stay up to date on the latest requirements and ensure that you are providing the highest level of electrical safety. Properly designed, installed, and maintained grounding and bonding systems are fundamental to electrical safety and reliability. A thorough understanding of the NEC requirements and best practices is essential for electrical professionals to protect people and equipment from electrical hazards. Furthermore, consider the impact of nonlinear loads on the grounding system. Nonlinear loads such as electronic devices and variable frequency drives can generate harmonic currents that can overload the neutral conductor and create voltage distortion. This can lead to overheating of the grounding system and increase the risk of electrical noise and interference. To mitigate the effects of harmonic currents, consider using oversized neutral conductors, harmonic filters, and properly designed grounding systems. Additionally, pay attention to the grounding of sensitive electronic equipment. Electronic devices are particularly susceptible to damage from voltage surges and electrical noise. To protect these devices, use dedicated grounding conductors, surge protective devices, and isolation transformers. Ensure that the grounding system for sensitive electronic equipment is separate from the grounding system for other equipment to minimize the risk of interference. Also, be aware of the potential for stray currents in grounding systems. Stray currents can occur due to improper grounding, unbalanced loads, or other factors. These currents can cause corrosion of metallic structures, interference with electronic equipment, and even pose a safety hazard. To minimize stray currents, ensure that all grounding connections are tight and secure, balance the electrical loads, and use appropriate grounding techniques. In addition to the NEC, other standards and regulations may apply to grounding systems, depending on the specific application and location. For example, the Institute of Electrical and Electronics Engineers, or IEE, provides standards for grounding and bonding of industrial and commercial power systems. Local codes and regulations may also have specific requirements for grounding systems. It is important to be familiar with all applicable standards and regulations to ensure compliance. Effective grounding and bonding are essential for creating a safe and reliable electrical environment. The information provided here is a general overview of grounding principles and practices. Always consult with a qualified electrical professional for specific design and installation guidance. Always consult with qualified professionals and adhere to all applicable codes and standards to ensure the safety and reliability of any electrical system. Remember to verify local requirements, as these can amend or add to the NEC. Always prioritize safety when working with electrical systems.